Welcome to lesson 32 of this Arduino C++ course, and today we're going to be looking at stepper motors again, so part 3, and today we're going to be looking at how to control multiple stepper motors at the same time. Now once again I'm going to be using micros for the timing. That's not delay microseconds, that is using micros instead of millis for timing. So if you're not familiar with that sort of method of controlling stepper motors, it would be worth looking at parts 1 and 2 to get an idea of how that works. Right, let's get over to the breadboard and see what's going on. So a bit of a cramped breadboard today. We have 3 stepper motors. NEMA 17, this is a NEMA 11, and this is a NEMA 17 with a gearbox on it. I've then got 3 buttons down here. Underneath this shield there is an Arduino UNO. Now I'm using a CNC shield. This can actually take 4 stepper motors. I just can't get my other stepper motor out of my model railway at the moment, so I'm just going to use the 3. But although I'm using the shield, the circuit diagram that we're going to look at is set up as if you're using individual stepper motor drivers. Right, let's have a look at this. So button 0, obviously we start 1 stepper motor, 2nd stepper motor, and the 3rd stepper motor. Now if you're wondering why they suddenly went off on a funny trajectory, if I move this one again, you'll see that when it gets to a certain number of steps, it actually triggers the other stepper motors. So we're going to look not only at how to control the stepper motors individually, but how one stepper can have an impact on other stepper motors. Now the other thing with today's setup, just to add a bit of variety, I've got the X and the Y steppers, that's this one and this one. They are using the A4988 driver. This is using the other driver, I think that is, what is this? That's an 8825 driver. They're all interchangeable. I must admit I find these easier to set up. These are supposed to be quieter. Again, as they're interchangeable, it's up to you which one you use. So going over to the Digital Town website, if you scroll down to lesson 32, as you can see, we have the circuit diagram and the links for today's code. Clicking on the circuit diagram brings up this bigger version. As you can see, I'm not using the shield. The circuit diagram has been drawn as if you're using individual stepper motor drivers. However, I am using the same pinout as the CNC shield uses. Now, if you do want to use a shield, this is was it an AliExpress one? They are £5.69 with the DRV8825, or they are, was it £4.69 if you want the A4988, or you can buy the unit on its own very, very cheaply. One of the nice things about these, obviously they have the built-in capacitor. The downside of these is it does make life a little bit more difficult getting to some of the pins. I would have preferred not to use it, but I don't have enough individual stepper motor shields for this project today. So going back to the circuit diagram, it's very, very similar to the last lesson where you have a step pin and a direction pin coming to each stepper motor. The difference that I've done for the sketch today is the enable pins here have all been directly connected to ground. The enable pin, when it's set low, set to ground, that enables the stepper motor driver to work. And as I want them working all the time, I'm setting those to ground, so the motor driver is available at all times. I could have connected these to another pin and set them high or low in code, but the way the stepper motor shield worked, it all started to get a little bit messy. Anyway, the other items here, I have 3 buttons. Again, these are connected to pins 9, 10 and 11. They have a pull down resistor. Now, I've had a couple of people have some issues with pull down resistors. One of the things to be aware of is that the connection to the Arduino goes on the same connection as the resistor that then goes to ground. The power is then supplied to the other leg of the switch. So what happens here is when the button is not being pressed, the circuit goes through this connection, through that resistor to ground. That means that the signal is held firmly down at 0, a low. When power is applied, when the button is pressed, that power goes straight to the connection, nothing goes through the ground, and immediately the line goes fully high. So that is how these step-down resistors work. I've got 3 buttons, just one for each stepper motor for this example. One other thing to be aware of is there is a requirement for a separate 12-volt power supply, and the more stepper motors that you add into the system, the bigger that supply needs to be. Now, because I've got no load on the stepper motors, I can get away. I think I'm using a 2 amp supply today. But if these were big stepper motors and they're having to move something quite heavy, you're starting to use a lot of torque, then you're going to need to make sure that your stepper motor power supply is large enough to power all of your steppers. Now, although in the example today I am just using 3 stepper motors, the code that we're going to be looking at today is expandable, so you could basically connect as many stepper motors as you wanted, sort of as many as you've got pins for. So let's get straight over to the Arduino IDE and start to look at the code. So sketch 1, and we've got 4 sketches today, is the usual test sketch. And this has been set up very similar to the last lesson where we were controlling a single stepper motor. So we had a step pin and a direction pin. The only difference now is I've got an X step pin, a Y step pin and a Z step pin. So if you like, I've given a letter to each of these step pins. You could name them whatever you want. At the same time, I've then got these 3 buttons that I've created, and again I've given them an X, a Y and a Z prefix because it then helps me to relate one button to the other. As before, we've got step micros and current micros, and the step timer is set to 1000. That is 1000 microseconds, so that's going to be 1 millisecond. This Boolean, as before, keeps track of what the next step needs to be. Coming down to the setup, again, very easy, setting up all of the step pins and direction pins as outputs, setting up all the buttons as inputs. Once that's done, I'm just going to come down to the main loop. And in the previous test sketch, when I was controlling a single stepper motor, we just had this one line. All I've done now is I have added in all 3 stepper motors. So instead of making a step for a single stepper motor, each of the stepper motors is going to take a step at exactly the same time. One thing to be aware of when you look at the desktop, the X stepper motor and the Y, that is the NEMA 17 and the NEMA 11, are both going to have 200 steps per revolution, so they will step in time with each other. The Z has a gearbox on it, so it is a lot more steps per revolution, so although it steps in time, it will look like it's going slower. Finally, we're also going to test all the buttons, and all they're going to do is serial print an X, a Y or a Z. And the whole goal of this is to make sure that everything is working at the same time. So let's get this code uploaded. So moving over to the workbench, we can instantly see that these 2 stepper motors are rotating at exactly the same time. That's because they're both 200 steps per revolution. This one, however, is moving slower because of the gearbox that's attached to it, and I currently can't remember what the reduction is. It is a huge reduction, I remember that much. So we can see from our initial wiring, all of the steppers are working okay. Now we're going to look at the buttons and an issue that will occur with these buttons. So what we're going to do is we're going to look at this serial monitor as I press these buttons, but I also want you to somehow keep an eye on the stepper motors as I press the buttons. So the goal is here, as I press the button, all it's going to do is send an X, a Y, or a Z to the serial monitor. So I can press the first button, we're getting some X's, second button we're getting some Y's, third buttons we're getting some Z's. But I'm just going to press just the Y button again, and I want you to watch especially the X stepper motor and the Y stepper motor, because the issue is very obvious. As I press the button, you notice how the speed decreases. Release the button, they speed up. Press the button, speed decreases. Now, the reason for this is actually to do with the serial monitor. And this is because I'm serial printing to the serial monitor, and I'm actually overloading the serial monitor. It's taking so long to write that character to the serial monitor. It's taking more than the difference in the step time between the different stepper motors. So what is happening then is that my timing is no longer dependent on this bit of code here. It's actually being held up by the time that it takes to serial print the value to the serial monitor. Now, this is very important with these projects, and what it means is that if you're writing something where your timing is using something like micros, very, very small periods of time, you need to be very, very careful sending information to the serial monitor while the stepper is running, because the steppers will slow down. So just be aware, keep your serial prints out of your code once you've, if you like, finished your testing phase. Now, another issue, if we just come back up to this bit of code here, I said that all the stepper motors are moving together. So we are getting our time. Once that time period has gone, we're going to get the value for the next step, and then I'm going to digital write to the 3 stepper motors. You would think that that means that they're all going to move at the same time. Well, they are and they aren't, and this is an issue depending on the type of project that you are doing. Now, it might sound weird. We don't tend to think about how long it takes to do a digital write. So the digital write is when we send the command to the Arduino pin and tell it to go high or low. Now, if you do a little bit of research online, you will find that it takes just under 3.5 microseconds to send that command. Now, that means that if we sent this at 0, this stepper is going to take its step 3.5 microseconds later, and this stepper motor is going to be taking its next step about 7 microseconds after the first stepper. Does that make any difference? Well, it depends on the project that you are working on. So just take a look at this. This is a lead screw. This is the sort of thing that you see on a 3D printer. Now, what I want you to imagine is a project where we are lifting something up, and maybe we need 10 lead screws. It's a big item that we're lifting up, and we're going to use 10 stepper motors to lift the item up. Now, if we run our code the way that I've got it at the moment, there will be, what's that going to be, 35 microseconds difference between when the first item tries to move the lead screw and the last item tries to move the lead screw. What that basically means is that all the lead screws will not be trying to lift as simultaneously as they could be. Now, for a lot of projects, let's be honest, if it was a 3D printer, it probably would make very little difference. But for some bigger projects, that can be crucial. Beds could twist, beds could jam. So if you want to lift multiple items, so you've got multiple lead screws that all need to act together, then you need to change your circuit diagram. So going over to our circuit, what you would do is instead of these all connecting to different pins, you would connect the same step pin and the same direction pin to all three stepper motors, or however many stepper motors you want to act as a single stepper motor. That way, when the step is sent, each driver will receive the step at exactly the same time, and so all the steps will be taken at exactly the same time. So today's lesson, we're going to be looking at using multiple stepper motors, running them independently. But if you needed to use multiple stepper motors and you want them to run totally in sync, then connect their stepper motor direction and step pins to the same pin on your Arduino. Otherwise, you are going to get that little sort of microsecond gap between them, and the more stepper motors you have, the larger that gap will be. Right, let's get back to running multiple independent stepper motors. So here we have sketch 2, and I'm going to use arrays to start to store the data. Now, if you're not sure about using arrays, you can go back to the Digital Town website, take a look at lesson 9, and that shows exactly how arrays are used. Now, it's not compulsory to use arrays. In fact, what you could do is if you took the code from lesson 31 with the limit switches, you could run each of the stepper motors independently, writing the same sort of code over and over. But for today's lesson, being able to use arrays just makes the code a little bit cleaner and easier for me to understand. It also makes it more expandable. So I'm using what's called a definition here. If you've only got 2 stepper motors, change that value to 2. It will change the size of all the arrays automatically. With the first array, this is the step pins. So instead of having to list 2, 3, and 4 as separate variables, I've now put them into the array. And the same with the direction pins. We've got 5, 6, and 7, and they are listed here. I've left the buttons as independent items because how you're going to control these things varies from project to project. So I thought I'd leave those independent for now. We still only need 1 current micros, but we need to have 3 different step micros, or at least the same number as we have stepper motors. That's because if each stepper motor is moving at a different speed, its timing is going to be different, and therefore this variable step micros is going to vary between each stepper. Now, the other thing that we have here, the stepper timer. Previously, everything was using the same timing. This time, I've got one set to 1000 microseconds, one at 6000, and one at 800. So the steppers are all going to be moving at different speeds. That means that the next step will be different from one stepper to the next. So we need an array for that. And also the direction later on will be changing independently. So we need to have an array that keeps all of those values. So this is just like running one stepper motor, but instead of keeping the values in independent variables, we're going to put them into an array. If you really cannot get on with arrays, and I would tell you to persevere with them, you can just go back to lesson 31 and just basically copy and paste the same code over and over, and basically change the variable names for each of your stepper motors. So don't panic it's not the end of the world if you can't get used to arrays. So moving down to the setup, again, I've left the old system in here, and that was about setting all the direction pins and step pins as outputs. All that's happening now is I'm going to work through my array, and for each member of the array, it's going to set the appropriate pin value as an output. And then as before, we've got the pins being set as an input. Finally, we come down to the main loop. And for this one, although I've left the buttons in there with that serial print, we're really not going to use them. The important bit of code that we're looking at is this little piece of code here. So before, we just had this bit of code and we went through each stepper motor one after another. This time we've got a for loop, so we're going to go round this loop here for the number of stepper motors. For each stepper motor, we're going to check if it is the time for that stepper motor to move. And don't forget now, because of our array, each stepper timer is different for each stepper motor, and that means that step micros is going to be different. If it's time for a step, we're going to set the value of the next step, do the digital write, set the step pin to its appropriate values, and then I'm going to update the timing of the step micros to the latest value of current micros. By doing this, you'll now see that all three stepper motors are moving independently at completely different speeds. So coming back over to the desktop, this stepper motor here, we had got it running at 1000 microseconds, whereas this one is running at 6000. So this stepper here is going to be turning 6 times as fast as the stepper motor here. It's a bit difficult to do a comparison with the Z because of the gearbox that it has connected to it. But as you can see, now we have 3 stepper motors running simultaneously, but all going in their own directions. Now, I could have set the code so that the steppers work together. So if this stepper and this stepper have the same speed and direction, they will move together. But obviously you need to be aware that there would actually be that 3.4 microsecond gap between these steps. It would look simultaneously, but technically it's not. Now coming back to the IDE, we can now see that we can move the 3 stepper motors independently, but now I want them to be triggered by the different buttons. So again, the arrays are all set up the same. This is all the same. Now, though, we're going to have a stepper target and a step counter. Step counter is going to keep track of exactly where the stepper motor is. This is exactly the same as was used in lessons 30 and 31. The only difference is that instead of storing the step target and step counter in an individual variable, now it's stored in an array so that it can store the values for all 3 stepper motors. I've also got a little bit of a debounce code in here just for the buttons that I'm pressing. Again, if you go back to, I think it's lesson 3, we looked at debouncing. So yeah, that's history. I'm not going to explain all of that. Right. Coming down to the setup, as you can see, setup is exactly the same as the last sketch. So now we come down to the main loop, and let's have a look at this code. Now, I've been using current micros. You'll notice current millis has been brought in. It's back, and current millis is just being used for that debounce of the buttons. So if any button is pressed, it gets debounced. Now, if we look at the code for the steppers, you'll notice here that very little has changed. We've got the for loop as before. We're then checking, the big difference is before we had the for loop and then we had the movement loop. The difference now is that we're checking is the stepper target not equal to the step counter? So in other words, we're setting a target that we want to get to. So let's say we set a target of 1000. The step counter will then start working its way along. Every time it takes a step, the step counter for that stepper motor is incremented, and it will keep moving forward one step until the step counter and the step target become the same. Now that is why at the beginning of the sketch, the step target and the step counter are all set to 0. So when the system starts up, it knows that the steppers are all, if you like, at their destination already. They're not going to launch off into a movement. So that is the code for controlling the steppers. Then we come down to the buttons. Now I'm going to use buttons. You could be using anything to command these stepper motors. If you're doing a model railway, this could be coming from a DCC command. Now rail, it would be a now rail command. This could be a command that's come over the serial monitor. I'm just using a button for the example. Use whatever you want, but this is how the code works. So for the X button, that is for the NEMA 17. What I'm going to do is when the button is pressed, it's going to check what direction the stepper motor is currently going in, and it's going to swap the direction. It's then going to set the direction pin. It's going to reset the step counter to 0, and it's going to set the stepper target to 6000. So what will happen here is when the button is pressed, the stepper motor will go off in the opposite direction to the last direction it rotated in, and it will keep going until it's done 6000 steps, which obviously is quite a few rotations. So that's the X button. When we come down to the Y button, this is the small NEMA 11. This time when I press the button, I'm going to change direction, but this time I'm changing the stepper timer. So in one direction, it's going to be 500 microseconds per step. In the other direction, it's going to be going at 6000 microseconds per step. So one direction, it's going to move pretty quickly, and the other one, it's going to move much slower. Once again, I'm setting the direction pin, setting my step counter back to 0, and my target for that smaller stepper motor is only going to be 2000 steps. Finally, we're coming to the gearbox one, and with this one, all that's going to happen is when the button is pressed, I'm going to set the step counter to 0, and I'm going to give it a target of 4000. So this is going to do 4000 steps in the same direction over and over again. Obviously, that doesn't look so far when you're using a geared down stepper motor. Now, one final thing to notice, I have removed all the serial prints out of this, because if there was a serial print statement in there, that will mess up the stepper motors that are currently running. It would knock their timing out. So I've now set the correct board. For those who you noticed, it was set to an ESP32, and I've now uploaded the code. Let's take a look at the workbench. Now, if you're wondering why I had that set to an ESP32, this code runs equally well on the ESP32 as it does on the UNO or any of the other boards. Right, let's have a look at this. So as we can see, everything is stationary because when the system starts up, the boards, if you like, all the stepper motors have reached their stepper target because their current position and their target were both set to 0 at startup. Now, if I press the X button, we can see that the stepper motor rotates in one direction. Now, if I press it again, it rotates the same distance in the opposite direction. Moving over to the NEMA 11, now, if you remember with that one, we're going to move in one direction at one speed. Quite a slow speed there. other direction, much faster, and the same distance. Finally, we come to the Z stepper, and with this one we can see that it moves a certain distance, and then I've got to press the button again. It's a very big reduction gearbox on there, so it doesn't seem to move far at all. Now, of course, that's all fine, but now what I can do is start to press all of these at the same time, and they will all move independently of each other. They'll move in either direction. And as you can see, they all now work really nicely together. Now, at this point, if you just want to use buttons to control your stepper motor movement or some other input, you're basically done. You now have the answer to your problems, and you can probably end the video now. Be nice if you click the like and subscribe. However, the next code we're going to look at is how one stepper motor's movement can trigger another stepper motor's movement. Now, the reason that you would want to do this, if you were trying to do something where you are creating some kind of mechanism where something needs to happen and then something else needs to be triggered at a certain point on the rotation, that's what we are now going to look at. So it might be something where you move a certain number of steps and then another stepper motor might push a locking mechanism across. Now, the code we're going to use here isn't just able to trigger a stepper motor. You could use it to trigger all sorts of other things as well. So let's take a look at Sketch 4. So Sketch 4, all of this is absolutely identical coming down. Setup is identical as well. So we just have some changes in the loop. Now, before we look at the main changes, one thing to be aware of, I have still left the buttons in here so I can fire up the different stepper motors with the buttons, but they can also be triggered through what is going to go on in the main loop. Now, the stepper motor that is going to be triggering the other stepper motors is the one with the gearbox. That is the NEMA 17 with the gearbox, which in my case in the array is in position 2. So coming back to the code that we had before, this is the normal sort of stepper movement one, but this time when it goes through the loop, it's going to say if Q, which is working through the array of steppers, if that's equal to 2, so that's the geared stepper motor, it's going to do a quick if statement. If that stepper motor has got to the position of 1000, so it's made its 1000th step in its distance that it's moving, I think it's moving, was it 4000 steps per press, something like that? Where's that bit of code gone? He says scrolling up and down. There we are, 4000 steps. So of the 4000 steps that it's going to make, when it gets to step 1000, it's going to set the direction of stepper 1. That's the small NEMA 11. It's going to give it a direction of 0. It's going to change the speed to 500. It's going to reset the stepper counter, and it's going to now give it a target of 6000. So every time the gearbox stepper motor reaches step 1000, it's going to trigger the movement of the small NEMA. When it gets to a target of 2000, so when the NEMA, the gearbox 1, stepper 2, or the Z1 in my case, when that gets to 2000 steps, it's going to reset the step counter for the NEMA 17, that is my X stepper motor, and it's going to tell it to move 2000 steps. It's not going to set a direction, so whatever direction it's already moving in, it's going to move 2000 steps. The reason for showing you this is it just shows how to use the stepper motor's steps to trigger something. Now, at the moment, we're triggering another stepper motor. This could have been an LED, it could be a sensor, it could be triggering an alarm, it could be doing anything you can imagine for your project. It might be interacting with a servo. So if you're building some kind of mechanism, this is how you now trigger when you want other items to move and interact with your stepper motor. So going back over to the breadboard, if I just press the buttons on the other two, they will behave just as they did before. I can change the direction and speed just by pressing those buttons. Now we're going to look at what happens when I press the Z. So now as I press the Z, I'm going to step. Now it's got to 1,000. Then you see it's got to 2,000 steps. Let's do that again. 1,000 steps, 2,000 steps. Obviously I can't serial print that out because it would mess the speed up. Now that impact of this stepper motor takes place even if I've pressed the other buttons. You can see that instantly it changes. You notice it more on this one than the other stepper motor. But what it just shows is that one stepper motor position can now be used to trigger events on other stepper motors or other items that you might want to use. So that's it for today's video. You now see how you can run multiple stepper motors at the same time, how they can be triggered independently, and how they in turn can be used to trigger other items. If you've got any questions, just leave them below the video or email me off the Digital Town website and I'll get back to you. And if you've got any other questions or things that you want in future videos, please let me know and I'll see if I can fit it into the schedule. Thanks for watching and I'll see you in the next video. Bye for now.